Hello, everybody. My name is Rithvik Suren. I'm from the Academy of Aerospace and Engineering in Windsor, CT, and today I'm here to present to you my project, Developing Autonomous and Adaptive Systems for Space Exploration Robotics with Neuromorphic Frameworks and Artificial Intelligence. Today, I will introduce to you the problem of AI to rover integration, along with my engineering objectives, methodology, statistical analysis, discussion, conclusion, and finally, acknowledgements. Humanity's greatest endeavor into the unknown is arguably space exploration. One of the great pieces of technology we've sent to extraterrestrial environments is Perseverance. Developed by NASA and sent to Mars, Perseverance was able to travel 17.7 kilometers in its first year, 88% of it autonomously. The two main tools that powered it were using artificial intelligence. AutoNav used the vision systems to help identify obstacles and engage in adaptive path planning, while AGIS, autonomous exploration for gathering increased science, allowed us to use less sample data to help derive more contextual information, identifying more mineral mapping techniques. A key part to recognize is that human-in-the-loop systems were still used in the decision-making process with the rover. Now, the current AI advancements in the field can actually boost exploration speeds from 1 centimeter per second to 1 meter per second by Dave Benedetti et al. And also, terrain segmentation could actually be improved to 98% in accuracy by Liu et al. However, due to the limitations on rovers themselves with computational resources and energy limitations, along with the requirements for a human to be in the loop through the process, this can prevent the future scientific exploration endeavors from creating fully autonomous rovers. In order for humanity to become an interplanetary species, creating these autonomous rovers is crucial in engaging in mass exploration. The current designs that try to address the issue of sophisticated AI to rover integration are fundamental system optimization and bio-inspired implementation categories. Now, the fundamental systems currently rely on open source tools and also commercial off-the-shelf resources. However, this can still push the balance of radiation since it can be a key factor in disrupting performance, as well as the energy limitations that are applied to the rovers. Model architecture optimizations, while being presented well, still can push the boundary and potentially harm performance in the real world, which would essentially work as dead weight. Now, when it comes to bio-inspired implementations, we can see that the researchers try to mirror the human brain itself. However, more and more complex variables that are involved in this, using Occam's razor, we can actually identify that there can be more areas for fatal error, and can be unreliable during a mission. I wanted to help address the issue of AI to rover integration using neuromorphic frameworks, or brain-inspired implementations. I wanted to combine the autonomous capacity that sophisticated AI can use with the efficiency and adaptivity of the brain. Using this key part called spiking neural networks, we can transfer the artificial neural networks that we already have into these spiking networks that can reduce the energy usage while still maintaining the sophistication and performance of the models. I intend to train a spiking neural network-based reinforcement learning model on NASA Mars terrain data and apply two major limitations to my agent. I first have a hardware limitation where I use a Raspberry Pi or a single board computer with my NASA code constraints following the NASA Power of 10 rules for constraining my program. My methodology consists of four main pieces: terrain curation, agent design, agent learning, and analysis. My terrain curation consisted of using the NASA MOLA dataset, which allowed me to construct an authentic environment that can be used for robust training. However, I ran into a roadblock. The Raspberry Pi can only handle 6 gigabytes max, but the dataset is 14 gigabytes in size. I helped work around this with an iterative batch processing script that I developed that can break down the dataset into chunks. I developed a composite diversity scoring script in SciPy that helped me find the most diverse piece of terrain in each chunk. With this, I was able to land on 155,521,038 Mars terrain records. With the composite diversity scoring, I actually achieved 2 times higher composite goal than my actual goal score. Now I had a compact, robust, and scalable terrain sample that I could then use to extract new feature parameters. After extracting and analyzing parameters such as standard deviation, roughness, etc., I was able to use this to curate and generate a new height map specifically for training. I constructed my agent with three main criteria in mind. Firstly, I wanted my rover to be articulated and have increased control. I applied a wheel-legged mobility system to allow us to navigate the varied elevation ranges. I also used a hierarchical control system to enable my rover to be fully autonomous and scalable for more and more systems, adaptively and robustly. I then have a complete set of instruments using two key components, stereo vision and IMUs, to help it have a good understanding of its presence in the terrain environment. So my agent structure in the hierarchy consisted of two main policies. One is a high-level policy and the low-level policy. The high-level policy uses stereo camera data to construct a simplified, sparse navigation graph. This graph is then used to identify the positions and derive the velocity heuristic commands. These are then sent to the low-level policy. The low-level policy uses these velocity targets and heuristics to help control 12 motors, which are then used to maintain stability with IMU data streamlined to the agent. Now, to set up my agent to be trained in this environment, I used the Raspberry Pi 4B Plus with a 4-core CPU and 6 gigabytes in RAM. This was still a constrained simulation tool that I used, which then paired with training simulations with PyBullet physics and the latest tools for spiking neural networks, SNN Torch. Now, to make sure the behavior of my agent is accurate and consistent with the current rovers, I used various regularization methods, such as joint torque and position, velocity acceleration, series elastic actuator torque, and much more. Here's where my favorite part of the project was, the art of hyperparameterization. I had to tune various variables such as LIF decay rate, regularization weighting, PPO clipping, and so much more to make sure my error rate of the model was the lowest possible. However, the roadblock was that finding the precise values as a human can be difficult, with all of them managing together with various different relationships involved. I used random search CV and grid search CV tools to assist me during this process, helping find insights on those relationships and using my human intuition to identify those relationships and tune it to the most optimal value. Now, I set up a computational apparatus to assess the resource efficiency of my model. So I tested for RAM usage, CPU time, and CPU utilization. My RAM usage was 11% compared to the 96.3% in conventional methods. My CPU time was 30 times faster than the current conventional methods used. However, now in CPU utilization, it may seem that the neuromorphic framework took more than the conventional methods. However, this neuromorphic framework uses 11%, an exact balance with the RAM usage, which is also 11%. This balance in both CPU and RAM is a neuromorphic characteristic that we call collocation, which is maximizing the efficiency of the model as shown. Now, I had to also validate the rover structure to ensure it could withstand the radiation simulations there. With this, I was able to use Fusion 360 to develop a CAD model and test it through the radiation simulations and displayed heat transfer and temperature readings. I was able to show how my model was able to stay stable throughout this process in both temperature and transfer of the heat throughout the time frame in the linear state space. Now, to validate the economic feasibility of this tool, I used the NASA software engineering lifecycle. I went from validating my project with experts in the field to in exciting talks with a private space company for simulated spacecraft testing of my tool. In conclusion, I developed a fully autonomous and adaptive control system using the spiking neural networks. With the spiking neural networks, I was able to increase the efficiency and neural collocation of my model with 30 times speed up in CPU time. With this efficiency, I aim to apply this in various different fields, also on Earth as well, with resourceful operations, balancing each resource while maintaining increased speed, but also making rovers more lightweight and compact using less hardware to do so. I'd like to enhance the current Perseverance systems on tools such as Aegis. In future, I would like to engage the vision systems as well and design a holistic rover with more and more systems. I'd also like to create
2-minute
a
warning.
physical prototype of my system and develop this into a physical environment, which can then be used for physical lab testing. In the future, I would like to also integrate this into a multi-agent system, expanding the capabilities for real-world performance with multi-agent systems. With the swarm robotics, I aim to increase the rate of exploration tenfold in the future. I'd like to acknowledge and thank my mentors and experts for their invaluable feedback and advice throughout my project development. Thank you.